Good morning, good afternoon, good evening, all of you. Welcome to the AESQ Process Control Methods Subject Matter Interest Group team's latest webinar entitled How to Choose Which Control Method I Need. I think you'll find this to be, like the other webinars, very, very power packed with some excellent information on how do we go about selecting the proper process control method to help control the risks determined through a PFMEA. So segues really nicely with that. So we've got a number of speakers. We're going to lead off today with Earl Capozzi, who's one of the founding members of the AESQ, going back to 2012, 2013 time period. And Earl's been very instrumental in AS 13100 in its writing, DPRV, as well as a supplier quality manager and discipline chief at Pratt & Whitney. Andrew Stout, our master black belt and co-leader of the process control methods team, is going to walk us through a good chunk of the technical aspect of this presentation. He is not unknown to you if you've been attending our webinars. You've seen Andrew in a number of them. And then myself, Pete Tatey, Pratt & Whitney Senior Fellow in Quality Engineering. So we will walk you through on how to go about selecting the proper process control methods. So with that, I'm going to turn it over to Earl. And go ahead, Earl, take it away.
Thank you, Pete. So the first couple of slides we'll go through relatively quickly. We want to make sure we have plenty of time to cover the topic at hand. First and foremost, we are recording this session, and the reason why is so we can post it on the AESQ webpage for those that couldn't attend today. It'll be available to them, and it'll also be available to you to use within your organization. If you have any questions, please use the chat feature. We'll be monitoring that and we'll try to answer them as quickly as we can. If for some reason we can't answer it today, we'll get a response to you. Very important, because we have a lot of material to cover, really please mute your phones and be respectful of everyone else. We don't want to have to stop the meeting and mute people or ask everyone to mute. So I really appreciate your help with that. Next slide. Which process control methods have you used before? So if you could take a minute, let's exercise that chat function. And if you can please enter some methods that you've used in the past. This helps us to understand where we need to focus more time on, or maybe go in more depth. I like to see all.
Just typing the number in will be good.
Yep.
For numbers.
It helps us understand what the audience knows. As you can see, I brought two big guns with me, Pete Tatey and Andrew, very well versed. I will say I studied statistics in school. I don't use it and apply it as they do. So they're the subject matter experts. So we can all learn, right? This course is really set up for everybody. So that helps us get us an understanding of where we're at and what the audience looks like. We appreciate that. Next slide, please. So process control methods is covered per RM 13006. The purpose of the RMs is to show you the different approaches. And if you spent any time with me, you've heard this before. It's a great resource for you. So we want you to use it shamelessly and steal shamelessly. It really does a very good job of exposing you and telling you how to apply the different process control methods. So, okay, very good. The next slide is what process control methods, SMIG groups, right? The purpose of the process control subject matter interest groups is really more in depth, and you can pick the brain of masters of process control, right? So we welcome you to join the interest group and get more involved. And if you're a subject matter expert, you can add value to and help the greater good, right, of process control and AS 13100. This is a big partnership, so this is one of the ways we get that knowledge base out there to use suppliers, and it helps us too. So once again, please join the interest groups. We'd appreciate that. Next slide. So here's some of the majority of the subject matter experts from the different companies that created the RM and the language in AS 13100. In many cases, they're the same folks that work on other teams like IQG teams. So you can see there's a mixed group of people from different companies and large organizations. You can see Pete Tatey leads the group. Andrew Stout's the co-lead. So if you have a specific question to the company that you're making parts for, you can use that list. So very important, where to get the supplemental material, not just RM13006, but you can get all the RMs and the different templates on the AASQ webpage. And as I said before, they're provided to you for free. So please use those RMs and take advantage of the templates and the different tools that have been created. You can also join the Control Methods Community of Practice on LinkedIn. So right now we're just under 430 members. So we would
445.
445.
That's
So
this morning.
I can be like the solicitor on the radio. Let's get it to 450. Can we get 5 people to join?
There
Next,
you go, Earl.
next slide. Hopefully you're familiar with this poster. We also have a video that explains the different tools and how they're all linked together. Today we're going to talk about process control, but it's really a living, breathing process, right? It's not like a first article where you're one and done and you get to check in the box. This isn't really a check in the box. This is to help use the data and the information you have to drive decisions to ensure you can deliver quality parts and ensure safety. So it's critical that you understand how the tools are linked together and how process control is probably one of the biggest tools, right? But that's what we're here to talk about today. Next slide. At least it's lagging a little bit. So this is kind of the lay of the land and the way RM13006 process control methods play into the life cycle of a part, from launching to continual production. So I won't spend a lot of time on this, and you can go back and reference this later, but you can see in yellow where it comes into play. Next slide. And once again, all the reference materials available on the AASQ webpage. Past webinars are also there. So and FAQs. So please take advantage of that. The next slide shows the different RMs that are available. And you can see right in the middle, RM13006 is what we're here to talk about today. And then you can see a little bit on the right side, the different templates that are also available to support process control. So next slide, I'm going to hand it over to Pete. I went through that relatively quickly because this is really the reason why we're here. So it's all yours, Pete.
Thank you, Earl. Excellent intro. So how do we choose the process control method we need? So looking at the pyramid, this came out of originally our AS 13006. Now in the reference manual, you'll see the foundational activities that every company is expected to have. Process control, which starts getting more into quality assurance, is built on a foundation of quality control. And that's where we provide our people training on standard work instructions, having capable measurement systems and so forth, TPM on equipment, 5S, 6S in our workstations. Now we can get into the methods of process control. Built on that foundation. This ultimately leads to product capability. Customers want capable products. And so we're going to focus on the middle, level 2, the 9 methods. So let's go down. Next slide. And we begin with error proofing. Error proofing in Japanese, poka-yoke, and I know all of you have heard of that term at one time or another, is the highest order of process control. And in the RTX world, we define 3 levels of mistake proofing or error proofing. A level 1 is you cannot possibly make the error that could cause a failure mode. Think of a 3-prong plug going into an outlet. There's no possible way you could get wrong polarization, which would cause the light bulb not to go on if you were to, you can't insert the plug in the wrong way. And so a level 2 would be like an alarm, a warning that would say to you, you've entered the error state, like you leave your key in the ignition and you open the door, the buzzer goes off to say, hey, you're about to make a serious error. You're going to lock yourself out of your car. Your reaction plan on your control plan says, you hear that buzzer, take the key out of the ignition. So level 1, level 2, and now level 3. Level 3 says the error has happened, the mistake has been made, the failure mode's happened, but we're containing it. We're preventing it from impacting the customer or the next customer down the line in the process. So these 3 are very important levels, and it's worth knowing. And when we start looking at improvements to reducing the risk from a PFMEA or corrective actions coming out of an 8D investigation, levels of mistake proofing ought to be taken taken into account. Next slide. Next, we'll look at, and of course, there's another webinar that we had last year called Non-Statistical Tools, and error proofing was a big part of that. So you can go on the past events web link and pull that down and use that in your internal training, as you can use this package too. This one's a bigger discussion. We typically provide, up to 16 hours of training around control charts for variable and attributes. And so when we look at SPC tools, statistical process control, basically these are what Dr. Donald Wheeler calls process behavior charts. They're monitoring the heart rate of a process output. You see an example here of an individual moving range chart. That was the subject of our last webinar, how to implement IXMR and target to nominal charts. And so the goal here is to understand whether or not the process is repeatable and whether is it accurate and is it precise in meeting what the customer wants. And so next slide, please. Yeah, so there's a number of benefits. By the way, it's 2024. This is the 100th anniversary year of the birth of the control chart, invented by Dr. Walter Schuhart out of Bell Labs, who had an apprentice working for him named W. Edwards Deming. So, but it was Schuhart who created the original control chart, the X bar and R. And financial benefits of process control and SPC tools. Again, this goes without saying. I am not going to read this off. I will point to the very bottom, Taguchi's loss function. If you might remember what that is, the further we get away from nominal, the more cost we get. The more cost impact it is to a customer. And again, that depends on the type of feature and what it does. But Taguchi's loss function is pretty important because it tries to drive us to work toward the nominal or optimum dimension. There's a lot of benefits for that. Helps to mitigate type 1 and type 2 measurement errors, for one, because you don't have borderline parts where you could call a part good when it's bad and call it bad when it's good. So again, that plays and interacts with Taguchi as well. In SPC, we look at the data that we're collecting. If it's averages, averages are going to follow a normal distribution, no matter what no matter what the individual values are that make up the averages. But if it's individual values that we're dealing with, and we do a lot in our business, we deal with a lot of individual values. Our lot sizes are small. And so, again, we talked about this in prior webinars. So selecting the correct distribution is important. But if you go back to the webinar, the 3 C's of SPC, we first said if you have a non-normal distribution, you better make sure you don't have assignable causes contaminating the data set, which is the reason why it's non-normal. Otherwise, we want to check to see if the data really does come from another distribution. Otherwise, we will make incorrect assumptions about the process capability. That's the fallout of having a non-normal distribution and treating it like normal. So again, something to consider as we analyze the data. Tools like Minitab really help us in this regard. Here you can see different shapes, Weibull distribution, and how that looks compared to a normal. Stability, though, is the most important part of any control chart. Stability gets into, can I predict where the next measurement will be? Is the process operating in a predictable manner? Is it not fluctuating all over the place in an unpredictable manner? And you can see the graphic on the left, these bell curves, they're different shapes, they're centered in different spots, different levels of variation versus the graphic on the right, where they all look to be around the same variation, lot after lot after lot. So that means the process control system is working. All the controls that go into making those lots, from your control of your equipment, your asset care, your materials, your raw materials, your temperature, your measurement systems, everything, your operators, setting up consistently from shift to shift, you can see goodness. And the process control system is working on the bottom right. Less surprises, as you would imagine. You're getting less surprises. So that leads us to this conversation about, well, okay, if you have a stable process, that's good. That's 80 yards of a football field, 100-yard football field. But what about process capability? Are we meeting what the engineer or the customer wants? And so process capability gets into indices, CP, piece of P, CPK, PPK. These are measurements, statistics that come from the data to tell us whether or not, basically, will the car fit inside the garage? And if it's off-centered, will that off-centeredness cause us pain? So we want to make sure a process is both accurate and precise in meeting the customer's expectation or tolerance limit. So you can see here, does the process have the potential to meet the spec limits? Is the process currently well inside the spec limits? No more than 1 in 500 are expected to be out of spec. Again, these are the stats of a controlled random process. Next slide. So let's see, that's not the next slide, is it? Okay, there we go. So here, yeah, you can see we've got this statistic called CP, and you can see in the upper left a histogram illustrated by the bell curve and the process spread. Well, that is well within the size of the garage, which is the illustration on the right. The car and the garage make a very nice way to explain this. And so we want that picture. That's the picture we're after. When we think about process capability, are we centered or are we well within the spec? And so CP is simply that distance between the upper and lower spec limit divided by 6 standard deviations. Standard deviation is the statistic we measure and calculate for the variability of the process. But we certainly first want to make sure that we have a stable process illustrated by the control chart on the right. We got to have that. And many times we see CP, CPK, all these capability calculations, but we don't see the control chart. And we expect to see the control chart. Process capability CP, engineering tolerance divided by the natural tolerance, and the standard deviation is estimated based on the short-term variation of the process. That's our average range. That comes from the bottom chart, the average range. And we divide that by a constant, D2. Now we're getting into the statistics of it, but this is all built into our software packages. But it is based on those short-term variables, which typically, think of a bag of M&Ms, machine and measurement. Those are the things that can change from one part to the next. Okay. So now let's look at this. CP is not enough. Which of these two processes is performing better? And what can you say about the CP in both of these processes? What would you say? Are they different? Are they the same? Is one greater than the other, less than the other? The CP value, which is the engineering tolerance, the upper spec minus the lower spec divided by the 6 sigma bell. Is it the same or different between A and B? Let's see, what do we got here? Are we getting any? Yeah, CP is the same. So, yeah, Joe, you got it. You nailed it. Joey, yep, you nailed that too. Good job. So they're both the same in this case, but one has got clearly a shift. One is biased from the nominal dimension or the target, and that's our problem. It's like pulling the car in too tight or too far over to the right or left, and now you're going to hit the wall of the garage. So obviously we don't want that. So when we look at the meaning of CPK, which is the cousin of CP, it takes into account accuracy as well as precision. CP is all about precision. CPK has the accuracy component. So it's going to look at the distance between X bar and the nearest spec and divide it by half the bell, 3 sigma. That gives us the CPK. And again, here are the formulae behind it. We had a webinar around this, what makes a good process capabilities study. You can download that and use that for your internal training. The slides are excellent, as well as these right here. So why do we need 3 formulas for the standard deviation? Well, if you look at the very first one, that's when we have a known population. And that's rare that we ever use that. The second one is based on the short-term capability of the processes I mentioned. In statistical process control, we want to get the long-term variation to equal the short-term. When we have that situation, and the long-term is measured by S, which is this classic standard deviation where all the values in a sample are utilized to calculate it. So it's going to have more sources of variation. But here's the caveat to that. If we're really controlling all those long-term nuisance sources of variation, temperature, raw material, people to people, setup to setup, standard work, shift to shift, these are the things that can impact the average and make it fluctuate. If you can control that, and you got good control of your measurement system and equipment, then the long-term and short-term will equalize. And it won't matter what capability index you use. And we talked about that in a couple of prior webinars. We spent a lot of time on that very subject. So really, it doesn't matter whether you CP or piece of P, PPK or PPK. But typically, PP and PPK are used when you have 100 to 200 readings, 3 or more lots, 3 or more setups. You're trying to understand the long-term variation over time. Again, if you got good process control, it should show a stable output for PP and PPK over time, and it should equalize CP and CPK. So control methods and comparing them, look at our basic run charts, pre-control, and control charts. Well, run charts and pre-control are non-statistically based charts. On a run chart, we may scribe a line as a warning limit. It could be, just a warning line that has a practical, it's in a practical situation where I think of the example in the reference manual where we go and add the viscosity level in a casting process. And we have a warning line that says if we get near that line, we need to add water. And that's a very practical thing to do. Control limits in that case may not be applicable, but that warning limit is very applicable to the casting process. So run charts with warning limits could be very useful. Pre-control looks at the spec limit and it takes the inner 50% zone and it establishes warning limits based on the inner 50% zone of the tolerance. Control charts are statistical limits based on 25 to 30 data points from a setup, and then we can calculate the upper and lower control limits, which are statistically based, and the Western Electric rules are going to follow. That gives us the ability to determine when to take action and when not to take action. But you can create those triggers with the non-statistical tools as well. So, and here we see what are statistical control charts, a graphical display of process performance over a period of time in time order. That's very key. In time order, the measurements are made in order. And so the upper and lower control limits represent the maximum and minimum values we would expect to see in this process, with of course the average being the expected value. So again, control limits give us the voice of the process. Spec limits is the voice of the customer. CP equals the voice of the customer divided by the voice of the process. Okay, so that's another way to look at it. Control charts separate noise, from signals. Is it a signal or is it a noise? And this is where it's important that the control charts be at the transformation process where the output is being generated. And it's used as a control method by the operator. It can help us determine whether we have a gauging issue going on or a tooling issue or any of the other items in this column. And so if the measurement system is not adequate, though, control charts aren't going to be very useful. And so it's important when we think about MSA, there are two ratios we look at, percent to tolerance and percent to study variation. It's that percent to study variation we want to be less than 30%, and that will tell us that the control charts will be useful. They will help identify when a key input is going out of control and we can take action on it. So that's an important interaction between RM 13006 and RM 13003. And here's some basics around control charts showing, what we would expect for the percent of values to fall within plus or minus 1 standard deviation, you're going to get 68%. Plus or minus 2, 95, and plus or minus 3, almost 100%, 99.73%. So, and it's broken up into these zones. You can see the A zone. We'd expect 1 out of 20 parts to fall in the A zone. And the B zone, again, 95% of values, 5% of the time they'll fall outside that band. If we start seeing 2 or 3 values in a row in the A zone, we know there's a shift going on. And that's something worth investigating because that shouldn't happen statistically. So that gets into the Western Electric rules and the probabilities associated with those rules. So we see our bell curve, our 68, 95, 99.73. And, 50% of all values would be expected on either side of the bell. And that's due to its symmetry property. Well, look at here, a third of all values are expected to be within, plus 1 sigma or minus 1 sigma from that mean and so forth. Again, I won't read all these off. You can look at this, but you can see where, how many points are expected to fall outside the control limit? About 3 out of 1,000. That's a pretty rare event. And that's why we would want to investigate a point outside a control limit, anytime outside an upper or lower, because that's a rare event to happen due to chance. It's probably due to an assignable cause. And that's what we're showing here with a control chart. Plus or minus 3 standard deviations was set by Walter Shewhart. He felt that was the right number of sigmas away that would mitigate us chasing special causes that aren't there and missing special causes that are there. Again, making a type 1, type 2 error using a control chart. Next slide. And these are the Western Electric rules that Shewhart and Deming came up with, pioneered this throughout the 20s and 30s and 40s. And number 1 is the most important one, a point outside 3 sigma. That we definitely want to investigate what's going on there. The other rules tend to be more or less cautionary. And, again, you might see a trend upward or downward. That might be due to grinding wheel wear, tool wear. Again, that's something that we want to be aware of that's going on. We might see a sawtooth pattern due to over adjustment on a process, operator chasing their tail. And we don't want that. Deming would tell you, don't go in and make changes just because one part is different from another. They're supposed to be different. As long as that difference isn't so big that it could hurt us. But we could add more variation to a process by trying to over adjust it. This one here is always an interesting one, the last one, test 8. That might be a gauge that's sticking. It might be the process variation is really, really so small compared to the measurement variation. And it could also be time to take down the control chart. But again, we got to be careful. That's not a random pattern. And we would want to understand, why do we get so many why are we getting this flat line? So these are all signals. They're signals alerting us that we might be entering an error state. Next slide. How do control charts maximize the potential of the process? When we're looking at here, like for instance, a comp tool note was added here. We did some compensation, and we had a part that was very high, and we did a compensation, and we brought it back to where we would like it to be. And then, of course, we had another issue and we did another compensation. And so a new tool type was brought in. So now we're gaining knowledge of the process. And because we're recording it, we're understanding the cause and effect behind these patterns. Some of these points we're going to eliminate when we go to calculate the true process capability and the true process control limits, because we don't want to have points that aren't representative of the process variation to be part of the control limit or process capability calculations. And that we can see as we go down another slide, we're starting to see this steady out. We're getting a steady state here. And again, by understanding what we need to do in terms of actions and changes that we made to the process that can help us make the process with less variation over time. That's really the goal. You start off, we're learning. And then as we gradually learn, we're getting reduced variation. Here we see another note, new type of locating system. So again, if we look at the standard deviation in each of those segments, it's getting lesser and lesser. And our margin of error is reducing. So we're predicting in a tighter band. That's a quality improvement. That is a quality improvement when you can predict within a tighter band. There are many types of control charts. In the variable world, you either subgroup your data or you don't. If you subgroup your data, you ask yourself, well, how big will the subgroup be? If it's like 2, 3, 4, 5, or 6, that's where we use an X bar in our chart. If it's 8 or more, then the range becomes very inefficient, and we use an X bar and sigma chart. Also, we might be looking at multiple measurements within a part. We might be measuring in multiple locations. That's where a 3-way type of control chart can be used. And we'll be having a webinar around that type of chart. That'll be coming up down the road. Individual moving range, 3-way. So again, you might have like a heat exchanger and you're measuring it in the height in 5 locations. And you're trying to determine the uniformity of across the surface. That's a perfect application of an IMRRS. And then there are charts based on individual measurements. The last webinar we did was all about that, implementing individual moving range and target to nominal charts. So check that webinar out. Variable control charts, variable data. Again, whether you're averaging or whether you're using individual values, in the reference manual, we have some great guidance in there. I'm not going to read this all off to you, just pointing you to go to the reference manual. But Andrew, putting this package together, pull that right out, making it very handy at your fingertips here. When would you use an X bar in R or an X bar in S? All right. I'm looking at my watch and we have a bit more to go. So I just want to make sure. And there we go. So Andrew, perfect timing. Andrew is now going to take us through a lot of the other reference manual control methods. So Andrew, I'll turn it over to you.
Okay, thanks, Pete, very much. Moving along in process control method number 3, run charts with non-statistical limits. So as Pete mentioned, in the reference manual, there's some really good tables that give you a good summary of when to apply these different tools, along with some examples to help make it more clear. So I'm going to show some examples here that will hopefully be useful as well. So on this case, we're talking about a run chart with some limits that are not determined based on the data, that are determined based on a function. And in this case, this was a process, or they can be used, first of all, for processes that tend to drift a lot, and control limits may send too many signals to investigate when you know the process can drift and can be allowed to drift with no adverse impact. So maybe in that case, a chart like this could be more useful, where you set a fixed limit within a tolerance. So in this case, we're looking at an example, something that I set up with in Excel way back in 2010, actually, for the fast hole EDM, or electron discharge machining of with a laser-based inspection on some turbine blades. And this is not the turbine blade we're looking at. We're actually looking at inspection of an artifact that was used. So it the idea being, when it gets into yellow zone, when the results get so high, then maintenance is called. And if it continues to rise and gets into the red zone, you need to stop and not produce parts that day. And this is something that the operator would check each day. And I was very pleased when I went back and looked in the system to see the results, and it was still going 13 or now 14 years later. So pretty amazing. So it's a simple approach, easy to use, easy to understand, and quite powerful as well. Okay, to create these and use them, there's a 6-step process that's shown in the reference manual, section 5.3. That takes step-by-step determining the variables, studying and quantifying the relationships, establishing the process limits, establishing how to what to do, like a reaction plan when you reach certain limits, operating the process, and then what to do when the process limit is reached, like the reaction plan. Okay, so that's pretty straightforward, section 5.3 of the RM. You can also refer to other webinars that we've done on this topic. Use of non-statistically based process control methods was done back in March of last year. That might be, if you want more information, that's another source to go and see on the past events on the AESQ website. Okay, on to the next process control method. This is next one is pre-control charts. And again, there's a section in the reference manual for application and examples. Pete already talked about it a little bit in the earlier charts, but pre-control can be used right away when you start production. You don't need to wait for determining formal control limits, because you're using the tolerance rather than the actual process data to determine your limits. So they're good for monitoring and controlling a process within the spec limits. They also work for unilateral tolerances, which are shown on the right. And typically half of the tolerance is shown with a green band, and the remaining tolerance is with yellow, and then out of tolerance is in red. And there's 3 methods that 3 different ways of applying pre-control. So the first method, called classical pre-control, involves taking a sample of 2 consecutive parts and then making a decision on that basis. And there's a table in the bottom right that shows a decision-making process, which I won't go through, but there's a way, do I need to take another part or not? Or do I need to stop and investigate? That sort of thing. The rules are defined for that. So then the example there in the bottom right is actually talking about the 2-stage pre-control, which is number 2, where you check 1 and decide if more checks are needed. And the third option is the modified pre-control, which is basically the formal control chart that Pete presented. Only now you're adding colored zones to that to make it a little bit more obvious that you're trying to hit the green zone, half the tolerance. And there may be some significant benefits to the quality of the parts, to the function of the part, and to the customer to be able to do that, thinking about the Taguchi approach. Okay, so starting CP should be at least 1. So we want to have a roughly capable process in order to use pre-control, and to make sure that we're not running into problems. We want to have some idea of control, pretty good control to start with. And we'll move along. So there are a number of advantages to understand, but it's also good to understand the disadvantages when you're trying to choose which process control method to use. So if you're thinking about doing pre-control, it's good to know the benefits, the drawbacks. So a number of benefits, advantages of it. It's easy to use. There's no calculations needed, really. Straightforward. No waiting for control limits. It's quick action signals. You don't need to take like big samples. It could be individual measurement decisions. Good for short runs that way. It gives you like a stoplight control where you make decisions right away. You can also use it if you've made a gain to your process using whatever tools, SPC, REDX, or whatever your improvement methodology. You can apply pre-control to sustain that level of improvement. It doesn't require a graphical record, but it certainly helps. The picture is worth 1,000 words, as they say. Can be useful to see what's going on better with a graphical output. So in some cases, the number 10 there, statistical control limits can cause confusion. If the person's not really familiar with them, some confusion between control limits and spec limits. And depending on the sample size, it may be some questions about that. So it may be some misinterpretation. So with pre-control, it's straightforward. What are the disadvantages? First of all, it doesn't monitor stability. That's something that we want to see, certainly that you get from the full control chart, which tells us, do we have predictability in our capability numbers? We need to know stability first, as we saw in the, you may have seen in the 3 Cs webinar just recently, or you can go back and look at that. Not so good if capability less than 1. Not good for detecting small process changes. If that's important for you, then maybe a full control chart is the way to go. Not as good for process improvement versus control charts. As we saw, as Pete showed, with the ability to capture improvements and tighten the control limits based on improvements to the process. This method doesn't give you that, right? So if you're looking to really maximize the capability of the process, then perhaps a control chart is better. Potential to increase variation by over adjustment, or also called tampering, right? So if you adjust after each part, then you'll end up with a wider distribution and more chance of making defects. Number 6, may need to develop the charts manually, perhaps using Excel or some other custom software, or done on paper. Certainly an option on paper would be a fairly easy way to start. Not so recommended for KCs, key characteristics. We'd like to see the control charts being used for that, because if the KCs are selected properly, there will be a benefit for the customer in driving those more to nominal, getting the good capabilities. So good to understand, what are the pluses, what are the minuses? Does it make sense to apply pre-control? There's also a webinar that was done April of last year, Power Process Pre-Control, that goes into more details on this topic for you. Next process control method is number 5, is life and usage control. So here, this method, it can be used where a process degrades over time and where the useful life is known. Some examples: the number of machine cycles for a cutting tool, the number of uses of a forging die, the runtime for peening media, and the time before chemical bath cleanout. You can all use this method. Use statistical studies or experiments to determine the interval. How often do you need to go in and make a change? So that's important to determine, and there's ways to do that. Moving right along, that was a quick one. Attribute control charts. Number 6. So variable and attribute control charts are used in many similar ways. And if you look at the table, most of the ways are similar for the left and the right. And well, where's the difference? Well, if what you're detecting is a little different, right? For variable control charts, it's changes in centering or spread. Whereas for attribute control charts, it's changes in a defect level or defective level. So defective means the whole part is considered defective, whereas one part can have many defects, right? So there's the differences there. So that's probably the biggest difference. On the left, you also have the advantage for under variable control charts to maximize the potential of the process, which Pete demonstrated. Attribute control charts, there's a number of different charts you may be familiar with, depending on what you're counting. If you're counting defects or counting defectives, and whether the sample size is constant or whether it varies. There's 4 basic chart types there that are shown at the bottom of the bottom right. And I won't go into details on that, but there is lots of detail, lots more information to help you select which charts to make sense. In table 3 in the reference manual, it's shown here. And a quick look at some examples. So the left side, we're talking about defects. The right side counting defective parts, basically. And the top 2 have constant sample size, so the C chart or the NP chart, constant sample. Whereas the bottom 2 have changing sample size. So if you look at the control limits shown in red, the red lines, they do vary, which looks very confusing for someone who isn't familiar with it. So ideally, you'd have constant sample size, but it may not be always possible. And but there are charts that can handle it. The U chart and the P chart can handle varying sample size. On to the next one, number 7. Visual process check and checklist. What's that all about? Sounds pretty obvious, but maybe I can add a little something. The visual process check is a confirmation of goodness, either before or during an operation. And the idea is to confirm something, usually involving a human, is done correctly. So, human factors, things can happen. In some cases, such as pre-flight checks, not really what we're doing, but a related business, certainly having a second person perform the check, doing the verification may be warranted. So there may be cases where manufacturing a part where human interaction is done, and there may be significant justification for a second person coming along to verify it. But ideally, we'd be using automation or error proofing methods to avoid issues.
Hey, Andrew,
Yes,
can I share an example that just happened?
please do.
On that, we had a case where an engine tube, when it gets welded, they check the ID by rolling a ball bearing through it and make sure that any obstructions aren't going to cause a problem. the bearing has to go all the way through the tube. That bearing got left inside the tube. What's used as a gauge got left. That's perfect example of visual process check now. And of course, that's part of the corrective action. How do you mistake proof to know that that bearing is not left? How do you ensure a dust cap is not buried inside an engine? How do you check that an O-ring has been installed before you assemble something? So these are all examples, but that one just came up recently, and an eagle eye is going out to talk about for folks doing that type of check, how are they going to assure a visual process check is in place? Thanks, Andrew.
That's a good example. Thanks for adding that. Appreciate it. Moving on. Number 8 is first piece check. Quick look at that. So here we check the first piece to validate the setup prior to full production. Generally, it's done for new production lot after maintenance at the start of a new shift. And in some cases, tighter limits or shifted limits are needed, as shown to the right, in the right two graphics there. Also, in some cases, multiple pieces may need to be inspected. So on the graphic to the right is when you expect to have a drifting process, and you may want to start it, make sure that it starts to the lower end so that you can be allowed to shift to the higher end without going out of spec. So it sounds like a very simple concept, but there are some variations on it that can make it more powerful, essentially. And moving right along, the test piece evaluation is number 9. And a quick look at that. So test pieces are used when it's impossible or impractical to measure something directly. Peening uses almond strips. The peening measurement gauge there shown in the middle of the screen to determine the peening intensity by measuring the amount of deflection on those little plates that are peened and then put on that gauge to validate. So a piece, if you look at the right-hand graphic there, is a part of a disc, turbine disc. So a piece is removed by wire EDM from the serrations on the disc, and that can be used as a test piece. So get the cat out of the way. Forgings may also be made with integral test coupons that can be removed without destroying the part. Okay, so there's a number of ideas there where test pieces can be used to avoid destroying the part. So now I'll hand it back to Earl to do the wrap up. And you're still on mute.
I double muted myself for safety. Thank you, Andrew. Next slide, please. So we're going to do a quick summary and then open it up for Q&A. And we're also going to squeeze in there some next webinars, what's up and coming, to give you the opportunity to understand. So where did we start our journey today? We started with number 1, error proofing. And then we went to variable data, right? Control charts for variable data, run charts, non-statistical limits, pre-charts. And then we rolled into forging and die and cutting. So life and usage controls. And there are other process control methods that can be covered there. We went through attribute data, and then we did visual and manual inspection processes, so visual process checks and checklists. And then we went into first piece checks and, went across some other process control methods. And then we just went through material properties. So next slide. So we kind of, in summary, created a little bit of a cheat sheet for different process control methods. So if you look at the one in yellow there, if you're steering process and prevent defects with warning limits, that's somewhat can be used for run charts, right? So the greens would obviously be best case, and then the yellows are, I won't say risk, but there's some risk in using those tools. They might not be the preferred method. And then the red would be, it's just not a good application for that process control method. I don't know, Andrew, or Pete, if you wanted to add anything.
I think you nailed it.
Okay.
Yep.
Next slide, please. So I know I'm going relatively quickly. The next slide shows you the up and coming webinars, right? So once again, we recorded this session. So all the webinars you can find on the AASQ webpage. And then if you want to join it live, you can see what's coming up, right? So useful but less known control chart methods is coming up. The next one after that will be dealing with non-normal data. That seems to come up a lot. And then process control and manual data collection, and how to ensure successful SPC implementation. So you can see the dates and times in the center column. We hope to see you there. And if for some reason you can't attend live, once again, you'll be able to get these at the AASQ webpage under webinars. I think we're getting ready for questions. Next slide. So now we'll open it up and we can use the chat function to ask questions. And then between myself, Andrew, and Pete, we will do our best to answer those. And if for some reason we can't, we'll get back to you. But I think we'll nail it.
We have one question on here so far. When the process is not stable in the long term, how is it good to calculate CP? When the process is not stable in the long term, how is it good to calculate CP?
Well, throw a quick one out there. CP will give you some idea of what's going on capability wise, but we don't like calculating CP or piece of P when the process is not stable, because by definition, it's not stable. Then there's assignable causes. And we want to eliminate the assignable causes. We want to understand what's driving the lack of stability. Stability, repeatability are the most important thing. And that leads to a highly confident capability index that gets calculated. You can put a lot of value in it. There are certain exceptions. No process is ever perfect over time. But I mean, again, we need to understand the sources of the instability. Then it would be worth calculating. Yep.
We could also say how unstable is it? Is the point just beyond the control limit? Like it's very close to being in control, statistical control, or is it way out?
Yeah.
Right? If it's very close, then your CP, CPK values, PP, PPK will be close to what they will be in the future.
Yep.
Right. And also you might want to say, are we looking at an early stage of data in an early part of the run and trying to get an idea for how it's going to be in the future. So we may recognize that our numbers are not going to be perfect. We're going to have some changes as we get more data. So that's another consideration.
Yeah.
Any other questions? Feel free to type something in the chat. We'll do our best to respond. Any of the 9 methods or some topic related to process control methods in general?
Now is your opportunity to get some guidance, so take advantage of it. We're not going to call you out, but we'd love to give you an answer.
Well, the questions are being thought of, again, emphasizing the point. There's a lot of excellent reference material for free. There has been such an enormous amount of energy put into developing a lot of the reference manuals and templates and, worksheets that are available to anyone on the supplementary material page. Please take advantage of that. You could literally create your training program from a lot of the webinars that we've provided. So we want you to do that. Always ask questions. Feel free if you don't think of a question now, but all of a sudden the webinar is over. Oh, I wish I asked that question. You can do that on the Community of Practice, the LinkedIn site. So, and you can get to that off the AESQ website under interest groups. Look for the tab called interest groups.
So the presentation will be shared. That was a question. And if they have a question, can they contact us directly? So as Pete indicated, the Community of Practice site on LinkedIn does have the ability to communicate, and we will answer the questions there. That's how that is done. In a few days' time, the presentation should appear on the AESQ website in the recorded form as well as the PowerPoint. Show us how we get access to the course. I'm not sure which course. Is that talking about the fundamentals course perhaps for AESQ, or wondering which course?
I'm not seeing those questions. Yeah, so I mean, if you go to the AESQ website, there is a tab for training, and you can, let's see here. Yes, there's a tab called training, and you have all the information on all the courses offered under that tab. There's a training information link, quality foundations, recorded webinars, things of that nature. Yeah, there's quite a bit there.
I don't know if I can copy and paste this into the. No. We just had a forum in Troll Hutton. Oh, it did let me. I'm going to put it into the chat.
Yeah. Good idea, Earl.
So there's QR codes there so you can see the different training that is offered by.
There is a lot of in-depth training provided by AESQ, PFMEA, Process Control Methods, MSA. They've got some very good instructors. Those aren't free, but they are worth it. They are worth it, and they're not terribly expensive either. Something worth looking at.
Maybe I can share that that training page. There's the AESQ site. Yep. AESQ.sae-itc.com is the site. Under training, a number of possibilities there. Training information.
Yeah, that's great.
Okay.
Also, before we close, a shout out to Becky Lemon of SAE, because she's always behind the scenes making these webinars work for us. And so I want to thank her for all the hard work she's done helping us deliver these valuable webinars. So
thanks, Becky.
Thank you, Becky.
She posted the link in the chat as well. You can click on that and go to the site. Thanks, Becky.
Beautiful. What do you say? We close up shop?
Sounds like a plan. Thank you, everyone.
Thank you, everyone. Have a great rest of the day. And please join our Community of Practice for Process Control Methods. Have a great.